Thank you, Ari. So I'm Tom, and I'm going to talk about the dark arts of binding C++ and Rust, or as I would like this presentation to be, because the reality is it's more like this, that we have a Rust mask on top of this fat C++ cat, and it is definitely not the hero we deserve, but it is the hero we sadly sometimes need. Before we start, here's just a brief agenda of what you're getting yourself into. I'm going to talk about some mid to low-level details about how programming languages interact at a binary level. If you know a little bit of x86 assembly, it's going to be helpful, but otherwise I'll try to make it understandable anyway. We'll dig into some code generation, both from the compiler side and some of our own crazy shenanigans, and then show some results and the lessons learned from it. Before we start, just a word about Embark Studios. We're a Stockholm game studio with a slightly unusual mission of blurring the line between creation and making. And on that mission, we have decided to use Rust as a super weapon. And we have probably heard many times that Rust is great, so I'm going to just move on and not talk about that. If you're here, you're probably a Rust fan. But in the process of making our game of shenanigans, we decided that we needed a physics engine. And the physics engine is the thing which allows those pictures you're seeing here. So it simulates the context between rigid bodies, soft bodies, the constraints between them, allows things like character interactions and so on. And we needed a robust solution that would be battle-tested. And while Rust crates exist, we went for something that has shipped in many successful games, which is NVIDIA physx, or we wanted to use it, but we didn't really know how. But physx is pretty great because it recently got open source, so you get to use for free a library which helped ship many games in the past. And it is now licensed under BSD 3 license, and you can actually get it on open source. On GitHub, sorry. So the problem is it's a C++ SDK, and it's not just a C++ SDK, it's a massive one. So according to Wikipedia, the project has been on for around 18 years, and during those 18 years, it's gotten a lot of functionality. And in terms of just API functions, there's 2,000 public ones, and they implement a lot of great features, so they exist there for a reason. So you get things like vehicle controllers that can just easily assemble things out of wheels and components and steering. You get characters and clothes, and even a special remote debugger, so you can just connect an application that shows you all the internal state of the engine to a running application, so you don't need to implement all the debugging features in your game. And that is pretty great. But before we dive into that, how does one in general talk to something compiled in a different language? It's actually a similar situation to something compiled in the same language, as long as it is a separate library. So if you download some crates from Rust, those will typically be compiled as very separate things, and then they need to talk to each other. And the API of programming them is one thing, but there's also the binary compatibility that they need to match. So there's a thing called an ABI, which is Application Binary Interface, and that specifies things like the struct layouts, the calling convention for how the various parameters to functions are passed in registers or pushed onto the stack, and a bunch of other things like name mangling and so on. And C++ doesn't really have an ABI. I mean, it kind of does, but it's only like de facto standard on each platform. So in practice, what happens is that the OS/compiler vendors, they agree on a specific set of conventions that they stick to. And then in practice, it is pretty fun. So you have a look at the function we have here, which just takes a few simple parameters, and we already have a discrepancy for where that C parameter is passed to. So in Windows, it comes in the XMM2 register, and Linux is XMM1 register. So that is a lot of fun to deal with. At least on a single platform, the compilers will be compatible just through the virtue of like Clang people and GCC people agreeing that, yeah, we should do the same thing, because otherwise it's insane. Yet still, sometimes bugs can result in differences between those calling conventions. And then some flags can potentially even affect that ABI. So for example, if you were to use this ZP flag on the Microsoft compiler on Windows, you'll get something which is completely incompatible with anything else which is written on Windows. And of course, you're still in a situation where Windows and Linux are incompatible between each other. So how would we talk to something like physx? And we would like it to be easy to maintain, so we don't have to patch things up every every time a new C++ standard comes out or a new version of the physx SDK comes out. We would like it to be robust so it doesn't break on some platforms. Like we don't want to support just Windows, we want it to be cross-platform. And we would like to be fast because those API calls will be plentiful. So you can, if you have tens of thousands of simulated units or objects in the scenes, we'll be making API calls for all of them in a single frame. And that's a lot of calls. So one potential possibility is to add the support for the C++ ABI to the Rust compiler, but that unfortunately involves making the Rust compiler aware of a whole bunch of C++ type system things and keeping track with it. And judging by bugs which exist between C++ compilers, that is not an easy task. So it's not really a reliable option for now, at least not the viable one. So another option is to create some kind of magic glue layer between the C++ and the Rust. So we'll be talking to this layer from Rust, and this layer will be talking to C++. And there's a tool in the Rust ecosystem which promises to provide a glue layer for at least C and a subset of C++. Now, I tried it, and unsurprisingly, a bunch of things exploded. Because while it managed to translate some things from C++, it could not match the ABI, which is kind of implementation specific and not very well defined. And then even if it did manage to support one platform, well, if it manages to output something that works on Windows, that'll probably break on Linux because it doesn't support that ABI. So we would likely need to have specific bindings per platform, per compiler setting, and likely still a lot of compiler support in Rust C. So not a great option either. So in practice, what is recommended is, and even recommended by the creator of C++, is that you create a stable C layer, and then you talk to that C layer. And while C doesn't have an ABI either, just like C++, at least it's a pretty old language. It is not changing very fast. It is not going to go anywhere. So in practice, a lot of languages which are not C can speak it, including Rust. So you just have a few decorations on your struct and specify the linkage, and it can talk to C. So the idea will be to create a stable layer for physx, where we would define a public C API that would just redirect all the calls to the C++ layer. And then we will talking to the C wrapper. The C wrapper just redirects things to C++, and hopefully everything works. Then we will take the C layer, compile it with the C++ compiler, which can understand both code bases, and give us a compatible C library that we can use. And we just link that with a matching matching set of Rust declarations, and hopefully things just work. And it is a lot of hoping, because things get tricky pretty quickly. And you have to be super careful when doing this. So for example, here's a simple struct containing an integer on both sides. And there's a function which just takes this struct and returns it immediately. The only difference between them is that the one on the right has a constructor. It's not even defined in this thing. And when you look at the compiled code for those functions, it becomes clear they're not compatible. So even though we're saying, oh, this is an extern C function, it's going to be used in a C interface, you actually get a very different result if you have a C++ feature in one of those structs. Luckily, some compilers will give us a warning. MSBC will, Clang will, G++ did not tell me that something is wrong. So they will tell you, you're going to have a bad time. Those functions cannot be used from C. But let's go deeper. Here's a very similar thing, where you still have a struct with just a single integer. And in here, the function does not return it. It just takes the integer from the struct and returns it as an integer. And the twist here is the struct has a copy constructor instead. And once again, we have a different code being generated, and even a pointer being accessed on the right side. So that will be fun, because if you called it unknowingly, you'll just get a crash, basically. And all the compilers have tried with all the sets of flags, including WAL, WExtra, -pedantic, and so on. They said this was cool. This is cool to use in a C layer. So we're going to have a lot of fun if we go and use that. There's also this, and this is a little spoiler in the title of the slide, but let's go through it. So this is a few structs which inherit from each other as a chain. And this is basically copied from the physx SDK. And what we're interested in is the size of the PX sweep hit. And I'm not going to ask you to calculate what the size is, because I don't think you can know the answer, because there is not a single answer. If you ask the compilers on Windows, you're going to get 64 bytes, and on Linux, 72 bytes. And I actually ran into this while trying to create this layer that would bind the physx SDK. And at that point, I just realized I hit a wall, and I needed to somehow deal with it. So we're in a situation where we cannot really use C++ types in the C wrapper. Even if it's a simple struct like a vector containing x, y, and z floats, because that already contains things like copy constructors and regular constructors, it will break the ABI. We don't even know the sizes of structs. So imagine taking or using an array across the interface where you don't know the size of the item. So you need to have some kind of function which will give you the index into the array at an unknown location. And then even then, you end up with a struct that you don't know the layout of. So you need to have accessor methods to get the specific fields. So that is going to be a great time. And running into this and kind of giving up on the situation just kind of gave me an idea that maybe there's something else we can do. Why bother having a single stable layer where you can have a layer per compiler, per platform, per set of compiler files? So you get a wrapper, you get a wrapper, everyone gets a wrapper, and we can actually generate that on the target machine that we're compiling for, and build that with the specific flavor of the C++ compiler in mind, so we'll be matching everything. And then we end up in a situation where the layout of structs and the ABI, the calling convention, actually are very well defined to that one specific set of things. And of course, to support all the different compilers and sets of flags, that will be a lot of work. And I didn't want to do that amount of work because that sounds crazy. So instead, I figured we can just ask the C++ compiler, where are the things? So you have a struct or class on the left side, and you can write a simple C++ program which will go over the fields inside that struct and ask, what is your offset from the start of the struct? What is the size of the field? What is the offset of the other field, and so on? And you can write this program once, and it will reflect and provide the offsets and locations of the layout on the target platform. So we will write this thing once and then just run it on every single target platform. It will generate or output the offsets for everything inside the struct. And that will create a little bespoke wrapper for whatever the C++ compiler thinks the layout of things are. And from that information, we can actually generate the matching C or Rust code. So this is already a basis for that special wrapper for every single person and platform and everything. And of course, writing that little reflection snippet, which will go over the fields and ask their offsets, will be a lot of work to do for every single struct inside the physx SDK. And of course, we can automate things if there is something which can give us information about the C++ compiler. And that is the Lib Tooling from Clang. And Lib Tooling is a really cool library which you can use to inspect the internal state of the compiler. You can get the AST, you can get some stuff after initial passes of semantic analysis. So you can get the list of structs, the list of functions, the list of members inside structs, and so on. And when you build a tool like this, you can actually make it work just like Clang does and support all the default flags that it works with. So for example, the include directories, a bunch of switches and preprocessor definitions, and so on. So you do it by creating this abstract syntax tree consumer, in which you actually basically have filters / queries, I guess. And you say, give me all the functions that start with a px prefix. And then it just calls your handler with all the information it has on that function. And in there, you can go deeper and dig into, what is this field? Oh, is it a basic field, or is it a struct field, and so on. And you can just kind of recurse and get all the information about the stuff that you're interested in. And then from there, you can eventually just go down to the smallest building blocks and figure out, oh, it's a bool, so I'll just output a Rust bool. It's a float, we'll output F32, and so on. So with this tool, we can actually generate that little reflection snippet that I had in the few slides back for every single struct in the C++ code base. In practice, it ends up being a bit more complicated than version, but it is essentially the same thing. For every single field, we end up just outputting the offset and so on. We have to inherit from the C++ structs, because if they have protected members, we could not get the offset off, but we can just kind of work around it in a fun way. And the nice thing is that this code generated by our tool, this we only need to run once, because we will run it on the target platform, and then we'll get different results. But this code actually ends up being platform independent. So even though it uses Clang, and somebody might run the generated code on GCC, it will still be still correct. Now, this was structs, and for functions, actually, the story is much simpler. So for every single C++ function that we're interested in, we will generate a very slim C function, which will just pass all the arguments to the C++ code and then pass the return back. Now, we need to be really careful to actually enforce that the structs passed in and the types are C types and not C++ types, as we saw before, because otherwise the compiler will go, I'll just send things in the wrong register and you'll crash. But we can do that pretty consistently by just going over the type information, remapping things as necessary, and then do some simple stuff like remap the overloaded variants to slightly renamed things and so on. And the nice thing is that this is also platform or compiler independent, so we will only need to do this once, and this is also output of that tool. So with those building blocks, we can actually get the full flow from the Rust code into C++, which will look something like this. So between Rust and C, there's basically no work being done. You just link them together, and the structs that you pass into the layer will be bit identical between each other, and that's just free. Then between C and C++, it's a bit more complicated because we have generated C structs which are bit identical with the C++, but the type system does not understand it. So everything aligns, but those are just foo and bar different structs of the type system. So what we do is just memcopy all the fields between each other, and then we call the C++ code. We get the result types and do the thing in reverse. Now, this might seem like some overhead at the memcopy level, but in practice, because memcopy is an intrinsic, the compiler actually understands that you are just copying field A to field A in the other struct and then just accessing that, so it knows it doesn't have to do that. So in practice, it just gets optimized out, and then this becomes an almost zero overhead layer. So using those tricks, we managed to generate this physx-rs crate, which gives this lovely example of a bouncing ball. And you can tell that no graphics programmers were harmed in making of this example. It is lovely. It gives you access to basically all the public functionality of the C++ SDK, but in an extremely unsafe and unergonomic way. So whenever you have things like inheritance, you have to cast the row pointers between seemingly unrelated types because Rust doesn't know that those should inherit from each other. So it's kind of ugly, but it works. And a nice little side effect of that is it is a generic C layer as well. So if, for example, Lua or Pascal or Haskell or something, they want to use physx, they can just use the same generated C layer and just steal it from here. And so about this machinery, which was running on top of Clang, the whole Lib Tooling thing, we only actually need to run it whenever we update the C++ SDK for physx or whenever we change the whole generator process. It is not fully cross-platform because it was a lot of work otherwise to make sure that it works. So for example, we have to have the Clang developer libraries installed on your system, and we would need to port the shell scripts to batch or PowerShell or whatever that is. But in practice, it doesn't really matter because we can just run that on some Linux/Mac machine and it'll be fine. So this whole pipeline will basically generate the C function wrappers and the little utility that will provide reflection over C++ types. And we put those things into a crate so that the end users don't need to worry about it. And then on the end user side, they just grab this crate, it contains those artifacts, and then just pass it into the actual build pipeline that the users execute. So as a part of that, they will actually build the physx SDK from source using the CMake and CC crates inside build.rs. So the entire C++ SDK is built with a known set of flags and a known compiler, and then we built the generated wrapper with the exact same set of flags, having reflected onto the layouts and structs of everything. So we have kind of finished building the wrapper library by reusing the utility, and we just glue everything together, and we have a working Rust solution. And that's basically that. And When it comes to using, well, the little caveat is that you wrap everything in unsafe because there's row pointers abound and no such thing as ownership tracking and lifetimes and so on. But the code is not that horrible to read. For example, you can actually use the structs for vector instead of heap allocating everything. So it is all right, even though it has some nasty stuff in it. But we don't like that nasty stuff, so we went and built a safer layer on top of that. Or Tom Solberg at Embark did that. It gives you a lot of ergonomics in comparison. It provides some safety. I would like to say all safety, but in practice, dealing with C++ is kind of complicated, and we basically work on this crate when we need more features. So we have a bunch of to-dos to clean up some unsafe stuff, but it does give you a lot of stuff. And it doesn't cover all the functionality, but it's fine to mix and match between the nice ergonomic layers and the unsafe horribleness. And we have a matching example of a bouncing ball, but this time from Linux. And then code using just the physx. It is lacking the lovely red with the unsafe on the side, but otherwise it's kind of similar. It doesn't have horrible pointer casts, but it does have one unsafe because we needed to use a row pointer in one place. But it's much better. And because we love open source, you can get it now from crates.io and from GitHub, and feel free to play with it, experiment with some physics and so on. So it is out there. So having covered that, one might ask, what do we do with this longer term? And ideally, I would like to say, let's not do this, because it's kind of horrible, and I would not want to be the person suggesting to integrate tons and tons of C++ into the Rust ecosystem. And we would vastly prefer a native Rust solution for things like this. But in the physx SDK took 18 years to develop for pretty serious reasons, and a lot of really good development went into it, including tons and tons of optimizations by skilled engineers. So it will take a while to get to that level when it comes to some libraries, at least. So in the short term, I would hesitantly say let's do this, and this is at least a viable way to provide a binding layer or glue layer between Rust and C++, which seems, at least so far, to be robust and reliable. We haven't seen it do anything unexpected at least. And please don't judge me by the code generator. I was learning clang and things as I was going. It is a bit messy and can definitely be improved. Maybe some stuff can be merged or collaborate with bindgen, for example. We've learned a lot of stuff in the process of doing that. So we have learned that binding Rust and C++ is not that difficult if you use the right tools. So if you use Cargo, you get all the amazing build process, which allows you to do things like building C++ software and then extracting libraries and all sorts of crazy stuff. And with Clang and Lib Tooling, you can get information out of the C++ code base and so on. So it's not that difficult. So if you're a game developer, for example, and you are afraid of using Rust because you fear you might be isolated inside the ecosystem because most of the stuff in game dev is written in C and C++, well, you can know that there is a way to actually get all those dependencies into Rust. So potentially it is an enabler for people who would otherwise not try Rust. So it's not all evil. And a little side effect of this setup is actually easier to integrate the physx SDK into Rust now than it is into C++. Because in Rust, you just say physx equals version inside your cargo toml, and in C++, you would probably spend, well, if you're using CMake, you might just use it, but if you're using anything else, you might spend between hours to days integrating the CMake stuff into your proprietary build system. I actually tried untangling the CMake build scripts from physx itself, but after half a day, I gave up. I decided the logic in there was just too complicated. So we can just use it like this. And probably the most important thing I've learned making this is that if you integrate a ton of C++ code into your otherwise pure Rust repository, you're not going to be popular among your coworkers. But it is a good motivation to turn the whole thing into its own crate and open source it, because then we just push it out and we have a pure project again. So we can live convinced that we are just writing Rust and everything is beautiful. But I apologize profoundly. And that was it. And please ask me at least 30 billion questions. not sure if you have time for 30 billion questions, but maybe at least 20 billion.
Yeah, great talk.
Thank you.
Tomasz?
Just Tom.
Tom, yeah, okay, sorry. Do you have any questions from the audience? Or you can perhaps...
So using your measurement in days or whatever to integrate the build system, how long would it take to use this for another C++ library?
This Rust crate, you mean?
Yeah? Or this
you
process?
mean redo the process for something else?
Yeah.
That depends which kind of edge cases one might run into. So the development of this was basically try to do something with the AST or information we have from Clang, run into a wall, then see, oh, what kind of other thing did they add? Oh, they have enums. I didn't have support for enums. Then add support for that and continue, and then run into another wall and so on. So it is very much an incremental thing, and I did take some shortcuts specific to physx. But in theory, one could extend this to a fairly general thing and support a decent subset of C++. I could imagine issues around things like templates and, I don't know, lambdas as parameters and so on, so more kind of abstract features. But a lot of libraries are written using a subset of C++, at least at the interface level. So maybe it would not be too crazy to have good coverage.
Cool. So if I... Ooh, very loud.
Sorry?
So if I would do something stupid like, oh, I want to use the standard library from C++ in Rust using your thing.
That'll be a bad time, because that's mostly templates.
Okay.
So you mentioned that you run part of the code to get the offsets and so on the target, which could be a limitation. Did you find the Clang tooling too limiting to get this limitation? I'm not familiar with the Clang, to get this information. I'm not familiar with the Clang tooling, but I mean, it is a limitation because you cannot cross-compile that easily, and the information is there in executable somewhere.
It was not a problem at all, actually, because all we need from Clang is just the information of which fields are in the struct. So this allows me to just write this kind of generic, almost copy-pasta-like code, like get the offset. If there's a field called foo inside your struct, I'll literally write add member foo, offset of foo, size of foo. So you just generate this thing which doesn't care about layouts at all. And then this is basically a C++ program that you run on the target, and just knowing the names of things inside a struct, that you could know if C++ had actually runtime reflection. This, you just run this small thing, and then you're done.
Okay, but that is code that runs at the build time or
Yes.
at runtime?
At the build time inside cargo. So every time you run cargo, it is potentially going to run that. In practice, it is all cached. So unless you actually change the set of flags you pass to your compilers or you update crates, it is going to just run once. But in theory, the entire pipeline is defined inside cargo, except the Clang thing with the Lib Tooling.
Okay. We can talk later.
Sure.
Yeah, we're creating a line here. So I maintain the V8 wrapper for Rust. So I've encountered some of these, V8 being the JavaScript engine. So I have encountered some of these problems as well. And you already spoke about templates being a problem. What about other things, such as logic in move constructors or destructors that depend on stack layout? Or have you encountered any of those?
Luckily, with C++, I did, with physx, I did not. So if I were to work with an SDK that had features like this, I would just have the automated tool which uses Clang to actually emit already some kind of wrapper inside the C++ side, or in the C layer, deal with the move constructors and so on to actually, well, not use them in the, just like in the current version, we generate C functions that don't take C++ inputs at all, but just mem-copying stuff around. Similar tricks might do.
Yeah, like, because I was saying I maintain V8, that's a strong statement. I haven't been able to update it for like years because I can't maintain the mapping, so I should talk to you after.
Sure.
Maybe using your library.
Any more questions? I think we're down to 20 billion minus 5.
The thing you mentioned with libclang looks similar to the internals of bindgen. Did you consider to contribute it to bindgen, make some custom bindgen, or make it available to the bindgen users to use your thing inside the bindgen?
I did have a look at BindGen, and it does use Clang as well. It is a Rust project, and it uses partial Clang bindings. I tried doing the same, but all the stuff that I needed wasn't really exposed to Rust yet. So maybe one could use a binding generator that should generate a Clang bindings you can use that in Rust. So, but on a higher level, I wanted to avoid making something which is too general, because my task or my idea was to bind physx, not knowing whether that actually would be feasible. So I just went all in. What is the quickest way we can get this thing, C++ SDK, to work with Rust? So not thinking about the larger picture too much. But now, having finished this, there is a bunch of techniques what one could use to make a larger, well, a more wide part of the ecosystem to work with Rust. I don't know how much work it will be, and I don't want to be the person that deals with C++ for too much of my time. So I would say there is potentially some ways to make it support, but pull requests welcome.
I'm asking because BindGen actually is trying to do the same, and BindGen is trying to generate the C++ layouts for the classes and inheritance, and I actually used it for the bullet physics bindings, and it actually worked at some level. So
that some level is the problematic
thing.
It
will be super cool if your work will be like merged with the BindGen, and it will be like actually worked. So
that'll be fun, yeah, if we could use things like bullet as well.
One last quick question. Let's thank Tom again.
All right, thank you.